this polar integral is going to be a little bit annoying. So let's find the area of the limacon r of theta equals 1/2 plus sine theta. So that's over here. And what I mean by area is I want everything except that loop-de-loop. So all that stuff. All right, and this is going to be an annoying one because we have to have, most of the time r is positive, but there's a section here when r is negative, and that's actually the loop-de-loop part in the middle. And it's always confusing to integrate when r is negative because not entirely sure, if it's going to come out positive or negative in the integral. So we're just going to have to deal with it though in this case because there's no way around it. All right. So the idea is we're going to make two integrals to be safe. So one integral is going to be from this angle to this angle right there. And so we go from here over to there. We're going to end up with this shape, which is the limacon. It's close enough that, I skipped over the loop-de-loop. And then we're going to subtract from that and make sure this area is positive, the loop-de-loop in the middle. And that should equal the limacon here with its loop-de-loop area taken out. All right, so that's the idea. Now in order to do that, we need to know what these angles are. All right, so you start at theta 0, we're at this dot. You go around, this top here is the peak there. You keep going around, this is at pi, so just a little positive. You go a little bit further, eventually get to r equals 0. You start doing the loop-de-loop and r is negative, and then r becomes positive again, and then you complete. All right, so really the values there when it switches, r is positive to r negative is when r equals 0. Right, so we need to know the value of that dot and that dot. What are the theta values? Well, that's when r is 0, right? So then if r of theta is 1/2 plus sine theta, then 0 equals 1/2 plus sine of theta is going to be the values of theta when that occurs. And that's the same as solving for negative 1/2 equals sine of theta. All right, now I had to look this one up. So this one ends up being 7 pi over 6. And this one here ends up being 11 pi over 6. And it's also going to turn out it's going to be useful. So if I kind of take this and move it over, this is repeating that one. This point right here is kind of the same one as this one and ends up being negative pi over 6. All right, so then, this is negative pi over 6, or kind of equivalently 11 pi over 6. And this over here is 7 pi over 6. So if I want the area of the limacon without taking out the loop-de-loop, what I can do is I can integrate from negative pi over 6 to 7 pi over 6. And the reason I didn't use 11, because I can't go from the theta value greater, I have to go from less to less, Negative pi over 6 is less than pi over 6, so I can go around like that. So putting that in here, this is the theta bounds. I want to go from negative pi over 6 is my lower bound, up to 7 pi over 6. 11 pi over 6 would have been a problem because then we'd have the bounds in the wrong order. The bottom bound would be bigger than the upper bound. Then we're going to have our r bounds, and so that one's going to be from 0 to 1/2 plus sine theta, and then we're integrating area, so it's 1. Then we have our r dr d theta. So that's going to be the entire limacon, including the loop-de-loop area. Then I'm going to subtract. And so now here it gets confusing. If r is positive, you're for sure going to get positive area out. But if r is negative, a little more confusing. So what I'm going to do, just to make sure that I subtract this positive area minus another positive area, I'm going to use absolute values. All right, so I'm going to have absolute value integral. The loop-de-loop is occurring between 7 pi over 6 and 11 pi over 6, I want to go from 7 pi over 6 to 11 pi over 6. All right, r is still going to go from 0 to 1/2 plus sine of theta. And then I have my 1 r dr d theta, close my absolute value. Now the reason this is okay is from 7 pi over 6 to 11 pi over 6, 1/2 plus sine of theta is actually negative. So the bounds here are in the wrong order. You're going from a 0 to a negative number, but it's negative the entire time, right? So it's either going to give out a completely positive or completely negative answer. It's not going to accidentally subtract and add pieces of the area. And then we're going to integrate the area and we're going to see what pops out. All right, so this is actually also annoying to do. So if you integrate this, you'll get r squared. Then you plug this in, you get the quantity 1/2 plus sine of theta squared. Then you have to use a trig identity to turn sine squared into the constant plus cosine of something. Right, it's annoying. But the hard part here is really setting it up. So I'm just going to write down the answer. So assuming you went and you did this integral, what you would end up with is 1/8 3√3 plus 4 pi. And then for this one, it ends up being 1/8 2 pi minus 3√3. Right, and it turns out 2 pi, which is a little more than 6, is greater than 3√3. So we actually didn't need the absolute values. This integral came out positive. The reason for that is you've got the bounds reversed, but then you're doing an odd function, and so it ends up coming out positive. It's annoying, so just to be careful, remember to use the absolute values. Don't try and reason it out yourself. But it did turn out that the absolute value of this is itself. Right? It's already a positive quantity inside there. All right, so I guess to finish it off here, we'll just put those together. Well, if we do that, let's say we have 1/8 times 3√3 minus 1/8 times negative 3√3. That's going to be 1/8 times, right, 3√3 minus negative 3√3 ends up being positive, so you have 2 times 3√3. And then the other bit, we have 1/8 times 4 pi minus 1/8 times 2 pi. So 4 pi minus 2 pi is 2 pi. So you actually end up with a plus 2 pi. And then that was times 1/8. Then you can simplify that a little bit more. So I have a 2 here, a 2 here, and a 1/8. So I can make this a 1/4. And it's 3√3 plus pi. Apparently is the area of the limacon minus its little loop-de-loop. All right, so that was fun. But going through it again, right? So if you can, always try to make sure r is positive the entire time. In this case, we couldn't avoid it, so we had to deal with it. And so we were really careful. So we found the area when r was positive the whole time, so 0 to a positive quantity. That was this piece. Then we subtracted, and we used absolute values just to be sure that we subtracted the positive area of the loop-de-loop in the middle. And then that had different bounds there. And that would give us the limacon without the loop-de-loop in the middle area. And if you actually go through and compute those integrals, you'll end up with these. And if you simplify, you'll end up with 1/4 3√3 plus pi. And yeah, so if you can, avoid it. But if you can't, this is how you would do it. You try to break it up into pieces and just make sure and be really careful that you kind of take positive area here minus positive area here gets the area that you want.